So we saw that in the simple black body approximation, our simplified model of the global energy balance, our energy balance model, gave us a surface temperature that was way too cold, an Earth temperature of 255 Kelvin, minus 18 degrees Celsius, a frozen planet. And we know that the problem is that we didn't include the greenhouse effect, which is responsible for warming the planet substantially beyond what it would be, what surface temperatures would be, if we were treating the Earth as a simple black body with no atmosphere. So we can actually accommodate the greenhouse effect, still using the approximate equation that we developed before, which told us that the surface temperature is equal to S, the solar constant, times 1 minus alpha divided by 4, that minus A, and that whole expression divided by B. We can still use that equation, but we are going to have to use new values for A and B, not the original values that reflect the assumption of a black body, but values of A and B that assume that Earth doesn't behave strictly as a black body, for the reason that the atmosphere actually absorbs some of the radiation that is produced by the surface as it tries to make it out to space. So we will change the values of A and B so that they reflect the existence of a greenhouse effect. And we will see that moving from the true black body approximation to this new approximation where Earth doesn't behave strictly as a black body, we'll call it a gray body, we can actually get very accurate estimates for the temperature of the surface of the Earth. Various values of these parameters A and B, the gray body parameters, have been used by different researchers in different situations. Since the gray body approximation is a linear approximation to a nonlinear relationship, the Planck radiation law, it is only valid over a limited range of temperatures, about some given reference temperature. This means that different sets of parameters might be used for studying, for example, the ice ages, where surface temperatures were substantially colder than today, than you would use, for example, for studying the early Cretaceous period, where we had a super greenhouse effect. It turns out that the choice is A equal 214.4 watts per meter squared, and B equals 1.25 watts per meter squared per Kelvin yield realistic values for the current average temperature of the Earth, T sub S, and gives us a value for something that's known as the climate sensitivity, a concept we'll define in the next section, that is consistent with mid-range model estimates of how sensitive Earth's surface temperature is to greenhouse gas concentrations. We will therefore adopt these values as our standard gray body parameter values, but we will also explore the impact of using alternative values a bit later. So let's now talk about the key concept of equilibrium climate sensitivity, sometimes just called ECS. We can rewrite the previous equation that we had for the zero-dimensional energy balance in a slightly different form, where we're going to replace that solar forcing term, which was the solar constant S times 1 minus alpha divided by 4, we're going to just replace it with some generic forcing F sub n. And that can vary over time. For example, the solar constant can vary over time. In fact, we know it has varied over time. So with that substitution, our expression for T sub S, the surface temperature of the Earth in the zero-dimensional energy balance model approximation, is just F sub n minus our parameter A, that divided by our parameter B. Well, we can rearrange that equation now to say that T sub S, the surface temperature, is equal to the quantity 1 divided by B, 1 divided by our parameter B, times F sub n, minus the ratio of A to B, where F sub n represents the total incoming radiative energy flux at the surface, as we said before, and that includes the incoming shortwave radiation flux from the sun, but we could also absorb into that term fluctuations in the downward long-wave radiation towards the surface due to greenhouse gas variations. Let us now consider the response of T sub s to an incremental change in that forcing F sub n. Now, since the second term is a constant, we simply have for any changes the change in the surface temperature, delta T sub s, equals the change in the forcing, delta F n, divided by our parameter B. Well, that allows us to rearrange things to get the expression, the change in surface temperature for a change in the downward forcing, delta Fn, is equal to 1 over B. A very simple result. That tells us that for a given change in forcing, the amount of warming of surface temperatures you'll get is simply equal to 1 over B. 1 over B is a measure of the sensitivity of the Earth system to a change in forcing, be it a change in the incoming shortwave radiation from the sun or a change in the downwelling long-wave radiation from greenhouse gases. So now let's assume specifically that delta F sub n does represent a change in downward long-wave radiation forcing associated with a change in CO2 concentrations relative to some reference concentration. Well, it turns out there's actually a nice approximate equation that tells us what delta F is in that situation. It tells us that the change in forcing associated with a change in CO2 is equal to the number 5.35 times the logarithm of the ratio of the CO2 concentration, the new CO2 concentration, to that reference concentration, CO2 sub 0. Well, now let us specifically assume that we are interested in the change in radiative forcing that results from a doubling of atmospheric CO2 concentrations relative to some baseline. Let's take as our baseline the pre-industrial period of 280 parts per million CO2. CO2 levels were roughly 280 parts per million prior to the Industrial Revolution. And so we might be interested in how much warming we get once we double CO2 concentrations relative to those pre-industrial levels. In other words, going from 280 parts per million to roughly 560 parts per million. The level that we'll be at in a matter of decades if we don't do something to stem our ongoing burning of fossil fuels. Well, in that case, where the CO2 concentration is double the reference concentration, we've doubled CO2 from pre-industrial levels of 280 to 560 parts per million, then that last term just becomes the log of 2, the mathematical logarithm of 2 multiplied by 5.35. And if you multiply it out, it gives us 3.7 watts per meter squared. That means the forcing due to a doubling of CO2 concentrations is just a little less than 4 watts per meter squared. We can define equilibrium climate sensitivity, ECS, or let's call it little s, as the change in temperature that results from a doubling of CO2 concentrations from pre-industrial levels of 280 parts per million to a level of 560 parts per million. Well, to estimate little s, we just have to combine this new result that tells us what the delta F is for CO2 doubling with our equation above that related the change in temperature to a change in forcing. And that actually gives us, for CO2 doubling, little s, the equilibrium climate sensitivity, how much warming you get if you double CO2 concentrations, is simply equal to 3.7 divided by our parameter, big B. The equilibrium climate sensitivity is the equilibrium warming we expect in response to CO2 doubling. In the simple case of the zero-dimensional energy balance model, It is readily calculated through that above equation. So in summary, in this lesson, we began to explore the use of theoretical models of the climate system, focusing on the simplest of all possible models, the zero-dimensional energy balance model. A simple zero-dimensional energy balance model, or EBM, can be used to estimate the surface temperature of the Earth, as well as the response of surface temperatures to changes in external, including human-induced perturbations. The model balances the incoming solar radiation absorbed at Earth's surface and the outgoing long-wave radiation emitted from Earth's surface. A simple linear approximation can be used in the zero-dimensional EBM to represent the outgoing long-wave radiation, leading to a mathematical simplification and a simple formula for global surface temperatures. Using the simplest black-body approximation for the outgoing long-wave radiation term gives a global surface temperature of about 255 Kelvin, 18 degrees Celsius below freezing, obviously way too cold. The gray body approximation provides a simple fix to the zero-dimensional EBM that incorporates, at least crudely, the atmospheric greenhouse effect. Using appropriate values of the gray body model coefficients, we can accurately predict both the Earth's surface temperature, roughly 288 Kelvin, approximately 15 degrees Celsius, and the response of surface temperatures to perturbations such as increasing greenhouse gas concentrations, which, for the most appropriate values of the parameters, yields a warming of about 3 degrees Celsius for a doubling of CO2 concentrations. In other words, a climate sensitivity or equilibrium climate sensitivity of roughly 3 degrees Celsius. Equilibrium climate sensitivity is a critical number because it's a universally used measure of how sensitive Earth's climate is to our ongoing pumping of greenhouse gases into the atmosphere. Now, we saw that 3 degrees Celsius for CO2 doubling is probably the most accurate estimate today of what that equilibrium climate sensitivity, or ECS, actually is. But there is uncertainty in those values, and with that comes uncertainty in future projections of climate change.